Let's solve some Leetcode today. So today we have Leetcode 994, that is rotting oranges. In this problem we have been given an m by n grid, and in this grid we will have 0, 1 or 2 number at any given cell. 0 represents an empty cell, there is nothing there. 1 represents that there is a fresh orange there, and 2 represents that there is a rotten orange there. And every minute any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So the fresh oranges are actually becoming rotten if they are adjacent to the rotten oranges. And then we have to return the minimum number of minutes after which no cell has a fresh orange. If this is impossible, return -1. So it means there can be cases where we actually get a fresh orange which does not become rotten in any case. So Leetcode has also given us an example. We have a rotten orange here and all of these oranges are fresh. So at minute 0, there is only one rotten orange given by the question itself. After minute 1, the adjacent oranges, the 4 directionally adjacent oranges, actually become rotten too, right? Remember that it is not working diagonally. So diagonal oranges are safe. It means the 4 direction simply means up, left, right and down. There is no diagonal edges. Now at minute 1 we have these bad oranges. At minute 2 the oranges adjacent to these bad oranges also become bad. So this and this orange is now rotten. On minute 3 this orange is also now becoming bad because it was actually adjacent to this one, right? So this is now bad. And on a minute 4, all the oranges are now bad. This one become bad because it was adjacent to this one. So at minute 4, all of these oranges are bad or rotten. So we will simply return answer as 4. So suppose that we have this 3 by 3 grid with the oranges. Now this problem can actually be solved as a graph problem. Well, it's a grid, right? It's a 3 by 3 grid and each of these cells actually represent a state or a place or a position. So we have a state, place or position, right? And in the question we have found a rule that is saying you can go in 4 directions from any given cell, which means we have a node and we have a rule that actually allows us to go from one node to another node. So let us try to draw this graph. Suppose we start from the middle cell. This middle cell is what? This is 1, 1, right? The coordinates of this cell is 1, 1. So we will have a node like this, 1, 1 representing the middle cell. Then this middle cell can actually reach this place or this place, right? So we can say we have an edge from 1, 1 to 1, 0, and we have an edge from 1, 1 to 1, 2. Similarly, we can go here also and here also, right? So we have an edge from 1, 1 to 0, 1, and we have an edge from 1, 1 to 2, 1. In the same way, from 0, 1, you can go here or here. So you will have an edge from 0, 1 to 0, 0, and you will have an edge from 0, 1 to 0, 2. In the same way, from 2, 1, you can go in this direction or in this direction. So you will have an edge from 2, 1 to 2, 0, and you will have an edge from 2, 1 to 2, 2. And then from 0, 0, you can go in this direction and reach this place, right? So you will have an edge from 0, 0 to 1, 0. Similarly, from 1, 0, you can reach 2, 0. Similarly, from 0, 2, you can reach 1, 2, and from 1, 2, you can reach 2, 2. So this is how the graph will actually look like for this particular grid. If you have any issues in understanding how we are able to create a graph out of a grid, please watch my video in which I am explaining everything about graphs, how you can convert anything into a graph. I will provide link in the description, or you can see a card popping somewhere here in the video. So now that we know we can solve it as a graph, let us try to solve it. Suppose we have a bad orange here. So this orange is a bad one. Now we can use two things. We can use either DFS or we can use BFS. If I try to use DFS, and I go in the depth, then I can reach here. So on minute 1, I will be making this orange bad, right? On minute 2, I will reach here. I will make this orange bad. On minute 3, I will reach here. I will make this orange bad. On minute 4, these oranges will also become bad, which works fine. Our answer right now is 4. But the DFS solution will break as soon as we have more than one bad oranges. Suppose I make this orange bad also. Now I run the DFS on this side. So I will go here. This will become bad. Then I will go here. This will become bad on minute 3, right? On minute 2, sorry. Then I will go back and then this will become bad. But this is where the issue is. Why is this becoming bad at this point? I had to go from here to here on minute 1, then here to here on minute 2, then here to here on minute 3. So this orange is actually becoming bad on minute 3. But we already have a bad orange here, right? This is a bad orange. It means this bad orange must have made this orange bad on minute 1. And this is where the DFS is breaking. This is exactly the reason why we cannot use DFS, because we can have multiple bad oranges resulting in multi-source DFS, and that multi-source DFS is not actually giving us right answer. There are places where you can use the multi-source DFS, but not in this condition, because you need minimum time to make all the oranges bad. And whenever you have something like minimum, the best approach is to use BFS. Why? Because BFS goes from one node in all of its children node and make them bad. at the same time. Then it goes to all of their children nodes and make them bad at the same time. It is going level by level. That means it will reach all the nodes in the minimum time. So how are we going to solve this question with the help of BFS, right? We will first of all have a queue, and inside of this queue, we will place all the bad nodes or all the bad apples or all the bad oranges in the starting. So we have this orange bad and this orange bad. These are basically 0, 0 and 0, 2, right? So we will have 0, 0 and 0, 2 in the starting in this queue. Usually we start with only a single node, but since we are starting from both of these nodes, we will have both of these in the queue in the starting itself. Then we will run a while loop. In this while loop, what we will do is we will find out the length of the queue currently. So length of the queue is basically len queue. So currently the length of the queue will become 2, right? So we will have currently 2. Then we will also have a time variable. So we will have time. Suppose I'm setting it to 0 initially. And now here I will simply make the time plus 1. So I'm incrementing the time here. I have these bad oranges and I'm starting to increment time. Basically I'm going to their children, right? And right now we have to process these two nodes, these two bad oranges at the same time, and then only we can actually have all of their children in the queue here. So we will have a for loop, and this for loop will run from 0 to the length. This is the length of queue, right? So we will run this for loop for all of these nodes, and now we will start popping oranges. We will pop the first orange. We will simply say orange is equals to queue dot pop or whatever function you need in your language. Then we will get this particular orange, right? So we will have like 0, 0 here. And now I'm not writing code because it will become very long. So here I'm saying now add all of X children in queue. So you pop the orange, you will take all of X children and place it in the queue. So we will have all the children here. And when we are placing the children, we can have a visited set. We can either store the children in the visited set also, so that next time if some other orange is connected to other orange, we will not visit that orange again. This is a simple thing in BFS. If you understand how BFS works, you will know the visited. And so we also mark them as visited. So we place them in queue, we mark them as visited. And also one thing that we need to do is we need to reduce the number of fresh oranges that we have. So somewhere in our code, we need to maintain a variable fresh oranges. In this variable, we will contain all the fresh oranges that is present in the 0 time. So when we are starting out, we have 1, 2, 3, 4. 4 fresh oranges. So in the starting, we will have 4 here. And here we will keep on decrementing the oranges as we keep on popping the bad orange and make its adjacent sides or make its children bad. We will keep on decrementing this fresh orange count. And since we are using BFS, guys, I will end up placing this node in the queue. This will be in the queue, and since this is also a bad node and I'm actually making sure that I'm running a multi-source BFS, I will take this node also and place it in the queue, which means I have 2 nodes which are actually becoming bad at time 1. And now once I have gone through these 2 oranges in my this for loop, I will go back again in the while loop. I will take the length of the queue again because these 2 will be gone. These 2 will be popped out. We will only have children of these 2, right? We will take the length again and we will increment the time. So it means the time at this point is 2, which is correct, right? On time 1, these 2 became bad, and then on time 2, these 2 will become bad, which is correct, right? So this is how the BFS will work. Now one thing you might be thinking is, why do we have this count of fresh oranges? The reason we have it is because we want to make sure that after running all the BFS, if we are left with any orange, any fresh orange, we will return -1, because that is written in the question. If there is any fresh orange, we will have to return -1. Otherwise we will return the time. So that is why we are keeping track of the fresh oranges and decrementing them as we go in the BFS. Here is an example where we can end up with a single fresh orange. So here we have 2 bad oranges, this one and this one, right? This bad orange will actually turn this orange bad, right? But after this, even if we go in any direction, here or here or here or here, we will not get any more bad oranges, right? Because there is no orange there. And it means that this orange, which is completely isolated, will stay fresh. And it means the count of fresh oranges will be 1 at the end, which means we still have a fresh orange. So we will end up returning -1. It is impossible to make every orange bad or rotten in this example. Now you might be thinking about how we are going to do this. How are we going to find out all of the children and mark them as visited? Well, we are going to use this graph, this particular graph, to find out which coordinates are basically the children, and we will just place them in the queue, and that's it. If you don't understand how this works, please watch my video on BFS and graphs, where I have explained completely how you do these kind of things. Graphs are super simple if you understand what they really are. So now I believe this much explanation is enough, and we are going to go in the code. So here is the code. First of all, we are starting with the queue as empty. Then we have a visited set in which we will keep all the nodes or all the oranges that we have already visited. Then we have this fresh oranges variable that will keep track of how many oranges are fresh. And here we are going through each and every cell of this grid. We need to find out 2 things. First of all, which nodes or which cell actually have bad oranges. 2 means bad oranges, and which cell have good oranges, the fresh oranges. So what we are doing here is we are figuring out the bad oranges or the rotten oranges, and we are placing them inside the queue, and we are making them visited already. And if we get a good orange or a fresh orange, we are increasing the number of fresh orange count in this variable. So we are basically setting up this initial configuration to start running BFS. Now here is a productivity check. If you find that there are no fresh oranges in the starting itself, every orange is a bad orange, or there is no orange in the grid itself, you can simply return 0. There's nothing to do, right? No need to run a BFS in this case, right? But if we do have fresh oranges, we will start running the BFS. So here I'm starting with the time equal to 0, and then I'm saying while the queue have some elements, first of all I'm increasing the time. So on time 1 this is going to happen. First of all I'm going to take the length of the queue at this current time. So at this current time the length will represent the number of elements in the queue. Then for this length I will run this for loop. Now in this for loop I'm popping the element from the queue. So I'm using the pop 0 because I'm simply using a list in the Python. So in order to pop from the start, you need to use this 0. So I will have the row and the column. I'm simply representing them as I and j. Then I know I can go in 4 directions from this particular cell. So I can go in up, left, right and down. So that is what I'm calculating here. In order to go up, I will simply subtract 1 from the row. In order to go left, I will simply subtract 1 from the column. In order to go right, I will simply add 1 to the column. And in order to go down, I will simply add 1 to the row. This is basic grid operations that you should know. And once you have figured out all these places where we need to go, we can actually start adding them inside of the queue. And now that we have all these edges, we can figure out whether we can add them in the queue or not. Now that we have all these cells, we can go to, now we will try to add them in the queue. We can only add these cells based on a certain condition. First of all, these cells should not be out of bounds. If they are out of bounds, we cannot add them, right? Then second condition is that if they are already in the visited set, we cannot add them. We have already visited them. And the third condition is that there should be a fresh orange on these cells. If there is no orange, why do we add them, right? So that is exactly what we are checking. In case of up, we need to make sure that this first element, the I-1 that we are changing, is greater than or equal to 0 because we are going up, right? So in the up condition, we might actually become negative. So that is why we are making sure it is within the bounds of the grid. Then we are checking if there is a fresh orange in this particular up cell or not. And then we are checking that if up is not invisited, then only we go ahead and reduce the count of fresh oranges by 1. We append the up in the queue and we append the up in the visited set. The same thing we do for left, right and down. So for left we are making sure that the column is greater than equal to 0 and these two conditions are same. Then for right we are making sure that the column is less than the end of the grid, that is maximum length of the grid, and then these two conditions are basically the same. And then for the down we are making sure that the row is less than the length of the grid. So these conditions are making sure that the given cells are within the bounds of the grid. Otherwise we will go out of bound and that is not what we want, right? And these conditions are basically the same. And here we are reducing the fresh oranges by 1. We are appending or adding the current cell in the queue and we are adding it in the visited set also. And now once we have gone through all the current elements in the queue with the help of this for loop, we will go back in the while loop with the new children elements already added in the queue. And after this we will again increment the time. So these new children element will be actually getting processed at the same time, and then the BFS will simply repeat for them also. And now after this entire BFS is done, here we are checking if there are any fresh oranges remaining, we will simply return -1. Otherwise we will return time -1. The reason we are subtracting this 1 from time is because this BFS will actually run for the last node also, right? For the last set of nodes which are already bad. So it means it will run one more time basically. So that's why we are subtracting 1 from here. Now we will try to run this thing and see what happens. So yeah, our solution runs in 0 milliseconds, beats 100% solutions on the Leetcode. I'm really not very sure of this number because nothing can run in 0 milliseconds. And good thing is that all of the 307 test cases are passing. So our solution is working. Now let us look at the time and space complexity for this solution. So the time complexity is order of m multiplied by n, and the space complexity is also order of m multiplied by n. So m multiplied by n simply means all the elements in the grid. M is the number of rows and n is the number of columns. So that's why we are saying order of m by n, because in the worst case scenario every cell in the grid might actually have oranges, right? In that case we have to go to each and every cell of this grid, and it means we will have to go through m by n elements. Same is for space complexity. Since we are using a queue to store all the elements, we might end up storing m by n element in some worst cases. So we are saying order of m by n for space complexity also. Now there are ways to make space a little bit more efficient, like we may not need to use visited set. We can just mark these 1 cells as 2 after we have gone through them. In that case we will not need to use visited set, but then again space complexity will still be the m by n because we will have to use queue. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments.